Scheduling. Chapter A. Scheduling the multi-level feedback queue. In this chapter, we will tackle the problem of developing one of the most well-known approaches to scheduling, known as multi-level feedback queue, MLFQ. The multi-level feedback queue, MLFQ, scheduler was first described by the Cobarto et al. In 1962 in a system known as a Compatible Time Sharing System, CTSS, and this work, along with the later work on multics, led ACM to award Cobarto its highest honor, Turing Award. The scheduler has subsequently been refined throughout the year of the implementation you will encounter in some modern systems. The fundamental problems MLFQ tried to address is twofold. First, it would like to optimize turnaround time, which, as we saw the previous note, is done by the running shorter job first. Fortunately, OS doesn't generally know how long a job will run for. Exactly the knowledge that the algorithms like SJF or STCF require. Second, the MLFQ would like to make a system feel responsive to the interactive users, that is, users sitting and starting at the screen and waiting for the process to finish, and thus to minimize the response time. Unfortunately, the algorithms like a round robin reduce the responsible for a time but are a tail for the turnaround time. Thus, our problems, given that we generally do not know anything about the process, how can we build a scheduler to achieve these goals? How can the scheduler learn as the system learns and the characteristics of the jobs it is running, and thus making the better scheduling decisions? The clocks. How to schedule without a perfect knowledge? How can we design a scheduler that both minimize the response time for interactive jobs while also minimizing turnaround time without a prior knowledge of a job length? Tip: learn from history. The multi-level feedback queue is an excellent example of a system that learns from the past to predict the future. Such approaches are common in operating systems and many other places in computer science, including the hardware branch predictors and caching algorithms. Such approaches work when jobs have pages of the behavior are thus predictable. Of course, the one must be careful with some such unique as they easily be wrong and drive a system to make worse decisions than they would have with no knowledge at all. 8.1 section MLFQ Basic Rules. To build a system, a scheduler, in this chapter we will describe the basic algorithms behind a multi-level feedback queue, although the specifics of the many implemented MLFQs differ. Both approaches are similar. In our treatment, the MLFQ has a number of distinct queues, each assigned from different priority level. At any given time, a job that is ready to run in a single queue, MLFQ uses priorities to decide which job should run at a given time. A job with a higher priority, that is a job a higher queue, is chosen to run. Of course, more than one job may be on a given queue and thus have the same priority. In this case, we will just use round-robin scheduling among those jobs. Thus, we arrive at the first two basic rules for MLFQ. Rule 1 is if priority A, priority B, and A runs, B doesn't. Rule 2, if the priority A and priority B and A and B run in RR. The key with the MLFQ scheduling therefore lies in how schedulers set priority. Rather than giving a fixed priority to each job, MLFQ varies the priority of a job based on each observed behavior. If, for example, a job repeatedly relinquishes the CPU while waiting for input from the keyboard, MLFQ will keep in a priority high as this is how an interactive process might behave. If indeed a job uses a CPU intensively for a long period of time, MLFQ will reduce its priority. In this way, MLFQ will try to learn about the processes as they run, and thus the use history of the job to predict its future behavior. If we were to put forth a picture of what the queue might like in a given instance, we might see something like the following. Figure 0.8, page 89. In the figure, the two jobs A and B are the same highest priority level, while C is the middle and the job D is the lowest priority. Given our current knowledge of the MLFQ works, the scheduler would just alternate time slices between A and B because they are highest priority jobs in the system. Poorest jobs C and B or D would never even get to run. Our strange. Figure 1. Figure 8.1 of MLFQ example. Q1, Q2, and Q3, Q8, A to B. Of course, just showing a static snapshot of some queues does not really give you an idea of MLF works. What we need is to understand how job priority changes over time, and that is a surprise only to those who are reading a chapter from this book for the first time. Is exactly what we will do next. 8.2 Attempt 1 How to change priority. We now must decide how MLFQ is going to change the priority level of a job and thus which queue it is on. And it is over a lifetime of a job. To do this, we must keep in mind our workload and a mix of the interactivity, the jobs that are shorter, overrun, and frequently relinquish the CPU, and some longer running CPU-bound jobs that need a lot of time to where the response time isn't important. For this, we need the new counts. We will call the jobs allurement, and the allurement is the amount of time a job can spend a given priority level before the scheduler reduces its priority. For simplicity, at first, we will assume that a allurement is equal to a single time slice. Here we are first to attempt to add a priority adjustment algorithms. Rule 3. When a job enters the system, it displays the highest priority at the topmost queue. Rule 8a. If a job uses up its allurement while running, its priority is reduced. That is moved down on one queue. Rule 4b. If a job gives up the CPU, for example by performing an I/O operation before the allurement is up and stays at the same priority level, that is, its allurement is reset. Figure 8.2 Long running job over time. Example 1 is a single long running time. Let's look at some example. First, we will look at what happens when there been a long time job in the system with a time slice of 10 milliseconds and with the allurement set equal to the time slice. Figure 8.2 shows that what happens to this job over time in a 3-queue scheduler. As we can see in the example, the job enters at the highest priority Q2, and after a single time slice of 10 nanomiseconds, the scheduler reduced the job's priority by 1, and thus the job is Q1. After running at Q1 for a time slice, the job is finally lowered to the lowest priority in the system, Q0, where it remains. Pretty simple, no? Example 2 is a long came a short job. Now let's look at the more complicated example and hopefully see how the MLFQ tried to approximate SJF. In this example, there are two jobs which is A, which is a long-term CPU, long-running CPU-intensive job, and B, which is a short-running interactive job. Assume A has been running for some time, and then B arrives. What will happen? Will MLFQ approximated as JF for B? Figure 8.3 on page 91 left, plot the detail of this scenario. Job A, shown in the black, is running along with the lowest priority queue, as would any long-running CPU-intensive job. B, shown in gray, arrives at time t equal 100 and thus is inserted into highest queue, as each runtime is shortly only 20 milliseconds. B completed before reaching the bottom queue, and the time slices and the A resumed running at a low priority. From this example, you can hopefully understand one of the major goals of the algorithm, because it doesn't know whether a job will be a short job or a long-running job. For it first assumes it might be a short job, thus giving the job high priority. If it actually is a short job, it will run quickly and completely. If it is not a short-term, it will slowly move down the queues and thus soon prove itself to be a long-running ball batch-like process. In this manner, MLFQ approximates SJF. Figure 8.3. Along came an interactive job. Two examples. Example 3 is what about I/O? Let's now look at the example with some I/O. As rule for B state above, if a process gives up the processor before using up its allotment, we keep at the same priority level. The intent of this rule is simple. If an interactive job, for example, is doing a lot of I/O, say by waiting for user input from the keyboard or mouse, it will relinquish the CPU before its allotment is complete. In such a case, we don't wish to penalize the job and thus simply keep it at the same level. Figure 8.3 is right, shows an example of how this works, and with an interactive job B, shown in gray, that needs the CPU only for 1 millisecond before performing an I/O, competing for the CPU with a long-running batch job A, shown in the black. The MLFQ approach keeps B at the highest priority because B keeps releasing the CPU, and if B is an interactive job, MLFQ further achieves its goal of the running interactive job quickly. Problems with our current MLFQ. We thus have a basic MLFQ. It seems to find a fairly good job at sharing the CPU fairly between long-running jobs and letting short or I/O-intensive interactive jobs run quickly. Unfortunately, the approach we have developed thus far contains serious flaws. Can you think of any? This is where you pause and think as deliver deviously as you can. First, there is problem starvation. If there are too many interactive jobs in the system, they will combine to consume all CPU jobs, and thus running jobs will never receive any CPU at the start. We'd like to make some progress on these jobs, even in this scenario. Second, a smart user could write their program to game the scheduler. Gaming the scheduler jamming refers to the idea of doing something sneaking to trick the scheduler into giving you more than your fairly share of the resource. The algorithm we have described is susceptible to the following attack before the allotment is used. Issue an I/O operation, for example, to a file, and thus relinquish to a CPU. Doing so allows you to remain in the same queue and thus to gain a higher percentage of the CPU time. When done right, for example, running for 99% of the allotment before the relinquishing the CPU, a job could nearly monopolize the CPU. Finally, the program any change its behavior over time. What was the CPU bound may transition to a phase of interactivity. With our current approach, such a job would be out of the log and not be treated like the other interactive jobs in the system. Tips: scheduling must be secure from attack. You must think that a scheduling policy, whether inside the OS itself, as discussed herein, or in a broader context, for example, distributed storage systems, I/O request handling, there is not a security concern, but increasingly in many cases it is exactly that. Consider the modern data center in which users from around the world share the CPUs and memories and networks and storage systems without caring a policy design and enforcement. A single user may be able to adversely harm others and gain advantage for itself. Thus, the scheduling policy forms the important part of the security of the system and should be carefully constructed. Section 8.3 Attempt 2 The Polish Boost. Let's try to change the rules and see if we can avoid the problem of the starvation. What could we do in order to guarantee the CPU-bound jobs will make some progress, even it is not much? The simple idea is here to periodically boost the priority of all jobs in the system. There are many ways to achieve this, and let's just do something simple through them or in the topmost queues, hence a new rule. Rule 5 is after some point period S, move all the objects in the system to the topmost queue. Our new rules solve the problems at once. The first process is guaranteed unstarved. By sitting in the top queue, a job will share the CPU with the highest priority jobs in a round-robin fashion, thus eventually receive service. Second, each CPU-bound job has become interactive. The scheduler treats it probably once it has received the priority boost. Let's see an example. In the scenario, we just show the behavior of a long-term job when competing for the CPU with two short-running interactive jobs. The two episodes are shown in figure 8.4 at page 93. On the left, there is a priority boost, and thus the long-running job gets starved once the two short job arrives. On the right, there is a priority boost every 100 milliseconds, which is likely too small of a value, but used here for the example. Figure 8.4 with value left and with the right priority boost. Okay, then. And then thus we at least guarantee the long-running job will make some progress, getting boosted in the highest priority every 100 milliseconds and thus getting to run up periodically. Of course, the addition of the time period S leads to the obvious question, what should S be set to? John Alsterhaus, a well-regarded system researcher, used to call such values into systems voodoo constant because they seem to require some form of the black magic of set them the correctly. Fortunately, S has the favor. It is set to high. Long-running jobs could starve too slow, and interactive jobs and may not get a proper share of the CPU. As such, it is often left to the system administrators to find the right value, or in the modern world, increasingly to automate the method based on machine learning. 8.4 Attempt better account. We now have one more problem to solve, how to prevent the gaming of the hour scheduler. The real culprit here, as you might have guessed, are the rule A and B, and which lets a job retain each priority by relinquishing the CPU before its allotment expires. So what should we do? Tip: avoid the voodoo constant. Other Alsterhaus law. Avoiding the voodoo constants is a good idea whenever possible. Unfortunately, as in the example above, it is often difficult. One could try to make the system learn a good value, but that too is not straightforward. The frequently leisure configuration file filled with the default parameters values that a second administrator can tweak is when something is quite working correctly. As you can imagine, these are often left unmodified, and thus we are left the hope that a default work as well in the field. This tip brought to you by our old OS professor, John Osterhaus, and hence we call it Osterhaus law. Figure 8.5 without the left and with the right gaming tolerance. The solution here to perform the counting of the CPU time at each level of the MLFQ, instead of forgetting how much of each element processed used at a given level when it performs I/O, the scheduler should keep track once a process has used each element. It is denoted to the next priority queue. When it uses each element in one long burst or the many small queue ones should not matter. We thus rewrite rules A and B to the following in single rule. Rule 4 is once a job uses up its time allotment at a given level, regardless of how many times it has given up to the CPU, its priority is reduced, that is, it moves down one queue. Let's look at an example. Figure 8.5 shows what happens when a workload tries to game that scheduler with the rules A and 4A and 4B on the left, as well as the new anti-gaming rule 4 without any prediction from gaming. A process can issue an I/O before each allotment ends, thus staying at the same priority level as priority level and dominating CPU time. With the value according to the in place right, regardless of the I/O behavior of the process, it slowly moves down to the queue and thus cannot gain an unfair share of the CPU. 8.5 The turning MLFQ, FQ, and other issues. A few other issues arise with MLFQ scheduling. One big question is to prioritize such as scheduler. For example, how many queues should there be? How big should the time slice be per queue? The allotment. How often should priority be boosted in order to avoid the starvation and account for changes in the behavior? There are no easy to answer to the question. And then thus only some experience with workload. For example, how many queues should be there and how big should be time slice be per queue. The allotment, how often should priority be boosted in order to avoid starvation, account for changes behavior. There are no easy to answer to this question, and thus only some experience with workload and the subsequent turning of the scheduler will lead to a satisfactory balance. For example, the most of MLFQ variance allows to the varying time slice length across different queues. The high priority queues are usually given the short time slices. They are comprised of interactive jobs after all, and thus the quickly alternating between them makes sense. For example, 10 or the fewer milliseconds. The low priority queues, in contrast, contain long learning jobs are CPU bound. Hence, longer time slices work well, for example, tenths of the millisecond. Figure 8.6 shows an example in which two jobs run for 20 seconds at the highest queues with 10 millisecond time slice, 4 millisecond in the middle, 20 millisecond time slice, and with 40 millisecond time slice in the lowest. The Solaris MLFQ implementation, the time sharing the scheduling class or TS, is particularly easy to configure. It provides a set of the tables that determine exactly how the priority of the process is altered throughout each lifetime, how long each time slice is, and how often to boost the priority of a job, and an administrator can work with this table in order to make the scheduler behave in different ways. Default values for the time are 60 queues, and with slowly increasing the time slice length from the 20 millisecond highest priority to fewer 100 millisecond lowest, and priority is boosted around every 1 second, so on. The other FLFQ schedulers don't use a table or the exact rules described in this chapter. Rather, they adjust the priorities using the mathematical formulae. For example, the free BST scheduler, for example 4.3, uses a formula to calculate the current priority level of a job, basing it on how much CPU process has used. In addition to usage is indicated over time, provided DI priority boost in a different manner and described herein. See EP Mouse paper for an excellent overview of such decay usage algorithms and their properties. Finally, many schedulers have a few other features that you might encounter. For example, some schedulers reserve the highest priority levels for operating system work. Thus, typical user jobs can never obtain the highest level of the priority in the system. So some systems also allow some user advice to help set priority. For example, by using the command line utility nice, you can increase or decrease the priority of a job somewhat, and thus increase or decrease its chances of learning at a given time. See the main page for more. Tip: use advice where possible. As operating system rarely knows what is best for each and every process of a system, it is often useful to provide interface to allow the users or administrators to provide some hint to the OS. We often call hint advice as the OS needs to necessarily pay attention to it, but rather might take the advice into the account in order to make a better decision. Such hints are useful in many parts of the OS, including the scheduler, for example, with NICE, the memory manager, for example, MADVICE, and MADVICE, and the file system, for example, informed prefetching and caching. 6.8 MLFQ summary. We have described a scheduling approach known as the multi-level feedback queue, MLFQ. Hopefully you can know why it is called that. It has multiple levels of the queues and use feedback to determine the priority of a given job. History is its guide. Pay attention to how jobs behave over time and treat them accordingly. The refined set of the MLFQ rules is spread throughout the chapter, are produced here for your reviewing the pleasure. Rule 1. If the priority A is greater than priority B, rule A runs, B doesn't. A rule that if priority A equals priority B, A and B run in round robin fashion using the time slice quantum length of the given queue. Rule 3. When a job enters the system, it is placed at the highest priority, the topmost queue. Rule 4. That once the job uses up its time allotment at a given time, regardless of how many times it has given up the CPU and its priority is reduced, that is, it moves down one queue. Rule 5. After some time period, S move all the jobs in the system at the topmost queue. MLFQ is interesting for following reasons. Instead of demanding a priori knowledge of the nature of job, it observes the execution of job and prioritizes its accordingly. And this way, it manages to achieve the best of the both worlds. It can deliver excellent overall performance and similar to SJF, STCF for short learning interactive jobs, and is fairly and makes progress for long CPU-intensive workloads. For this reason, manual stems include the BSD Unix derivative, Source and Windows NT, and subsequent Windows operating systems uses a form of the MLFQ as their base scheduler.